Hey guys, my name is IBM and I welcome you to my YouTube channel. This is going to be lesson 5, I think, of Electricity and DC Circuits. In this lesson, we shall basically deal with, especially we shall be dealing with e.m.f in relation to internal resistance and the terminal PD. In this lesson, we shall talk about combination of cells. We shall see the effect of internal resistance on the power emitted or power delivered by the battery to the external circuit. And most importantly, we shall explore more complex and simpler further examples in electricity and DC circuits. So basically, there is nothing much to explore in this lesson apart from relating the EMF to internal resistance and relating the internal resistance to the power delivered by a battery, and also looking at combination of cells in a circuit before we can explore the concepts of Kirchhoff's laws in lesson 6. So let's first deal with lesson 5 to gain a lot of confidence with the circuits so that we can now use these concepts in lesson 6 to deal with the Kirchhoff's laws of DC circuits. So remember, we are dealing with electricity and DC circuits, and this is going to be lesson 5. Okay, so like I said, we are going to start with EMF and internal resistance. So let's start. So have you ever wondered why is it that when a car engine is started, or when you start the car with the headlights switched on, the headlights sometimes first dim? Devices, batteries, power supplies may have what we call internal resistance, which we are going to explore in this lesson or in lesson 5. So when a car engine is started with the headlights switched on, the headlights sometimes dim. You can try to observe this, especially at night. Turn on the headlights or switch on the headlights of the car and then start the engine. You notice that they will first be dim, they will sometimes first be dim. And this is only because the car battery has some resistance. The car battery has some resistance. And by the way, all power supplies have some resistance between their terminals. All power supplies have some resistance between their terminals. Batteries, cells, and so on and so forth all have some resistance between their terminals. And the resistance between the terminals of a power supply is what we are going to call the internal resistance. The resistance between the terminals, the positive and negative terminals of the power supply, is what we are going to call internal resistance. So how do we define internal resistance of a device? For example, for examination purposes, internal resistance can be defined as the resistance of a battery in a series with an external circuit which accounts for the losses of energy inside the battery. So the internal resistance of a battery is the resistance of a battery in series with an external circuit which accounts for the loss of energy inside the battery. Of course, we can't talk about internal resistance if there is no current delivered to an external circuit. So the battery must be in series with an external circuit. And this is the resistance which accounts for energy losses within the battery. The resistance of a battery which accounts for energy dissipated within the battery. The resistance of the battery the resistance which accounts for heat dissipated within the battery, that is going to be the internal resistance. The resistance of a battery in series with an external circuit which accounts for the losses of energy inside the battery. So the internal resistance entirely accounts for the energy losses within the battery itself. That's what we call internal resistance. So the internal resistance causes the charge circulating in the circuit to dissipate or to waste some of the electrical energy in the power supply. Because the charge is supposed to gain its energy from the power supply, but because the power supply has some internal resistance, then the charge is going to dissipate some of the energy it has gained within the battery onto this internal resistance inside the battery. So this means there will be a PD across the internal resistance of the battery. That means not all the energy the charge gains from the battery is taken to the external circuit. Some of it is wasted within the battery itself. So that is what we call internal resistance. So like I said, all power supplies have some internal resistance. And that internal resistance is the one which is going to cause the charge saturating the circuit to waste some electrical energy within the power supply itself. The net effect will be that the power supply becomes warm or it heats up. So this is why the power supply becomes warm when it delivers the current. So sometimes when you touch the battery after it has been delivering a current, you may notice that the battery has become warm. Then why is it becoming warm? Yet it's supposed to supply energy to the external circuit. Some energy is wasted within the power supply itself. That is due to the internal energy, due to the internal resistance of the power supply. So how do we obtain internal resistance of, say, a battery or a power supply? How do we obtain the internal resistance of a battery or a power supply? I want you to recall that if no current flows in a circuit, we saw it as an open circuit. I think that was lesson 2, if not lesson 3. If no current flows in a circuit, we call that circuit an open circuit. And the PD across the terminals of the battery, we said it should be the same as the EMF. So if you connect a voltmeter across the battery, when there is no current flowing, the voltmeter gives a value which is equivalent to the EMF. However, if the battery is supplying a current to an external circuit, maybe the switch is closed and the circuit is complete, when I connect a voltmeter across the battery, it is no longer going to give me the EMF. However, it is going to give me the PD which is given to the external circuit, which we shall later on call the terminal PD. So what I'm saying is very simple, that if no current is in a circuit, if no current flows in a circuit, it's called an open circuit if there's no current flowing. And the PD across the terminals of a battery in an open circuit is called the EMF. So if it is an open circuit, there is no current delivered, maybe the switch is opened, the PD across the terminals of the of the battery is just the EMF. When I connect a voltmeter across the terminals of a battery when there is no current, the voltmeter gives me the EMF. So I can try to sketch this here. If I have a circuit such as this one where I have a cell and the switch is open, I have an open switch, and let's say I have a resistor in the circuit. So the switch is open. If the switch is open and I connect a voltmeter across the battery or the cell, whatever the voltmeter reads is not the PD across the resistor because the switch is open. This is an open circuit, no current is flowing. And when no current is flowing, the reading of the voltmeter will instead be the EMF in that case. So if a voltmeter is connected across the resistor, when a current is flowing, the PD across the load VR is called the terminal PD. By the way, when I transfer the voltmeter to this position here, when the switch is opened, the voltmeter will give no reading. But when I put it across the battery, it will give a reading, which is the EMF. However, if I close the switch, the voltmeter will give a value which is less than the value it gave before when the switch is opened. So, if a voltmeter is connected across a load or a resistor, when a current is flowing, the PD across the load is the terminal PD. So, the reading it gives when the switch is closed is no longer the EMF. Even if I don't transfer the voltmeter to this position and I leave the voltmeter to its original position, as long as the switch is closed, if I close the switch and the battery is supplying a current, then the reading of the voltmeter is going to be less than the EMF. And what is going to be reading is the PD across the resistor R, which we shall call the terminal PD. So we now know the EMF, there is no current being supplied. And the terminal PD is when there is a current being supplied. So the PD, which is going to be called V subscript small r, is going to be the PD across the internal resistance R of the battery. which we shall commonly call the lost volts. So because the battery has some resistance, which I'll call internal resistance, which we call small r, there is some PD or some energy lost within the battery due to this small resistance R. And that PD is going to always be called the lost volts. And that is the PD which accounts for energy loss within the battery due to its internal resistance. And therefore, because without any current being supplied, the EMF was E. When a current is supplied, the PD, the reading of the voltmeter becomes VR. It means V subscript small r is lost. But by conservation of energy, it means when I sum up this with this, I should be able to get the EMF. Because the sum of these two should not go beyond the EMF, or it should not be less than the EMF, because energy must be conserved. So by conservation of energy, therefore, the EMF is going to be equal to the terminal PD plus the lost volts. So if a battery has some internal resistance, many times you will see the battery drawn like this. So it has internal resistance and it has a terminal, a PD across, or a PD due to its small resistance. And we are saying the PD across the outside resistor is going to be VR, which is going to be called the terminal PD. But I'm saying we can get the same value if we connect the voltmeter between these 2 points. It is the same thing. Connecting the voltmeter between these 2 points, it will still be giving me the PD outside the battery, which is still the terminal PD. So the PD across the external resistor is called the terminal PD, and by conservation of energy, if there is no current being delivered, the EMF is E. When the current is delivered, the reading of the voltmeter is V subscript R. That means something has been lost, and what is lost is V subscript small r, which is the lost volts. Therefore, by conservation of energy, we say that the EMF equals to the terminal PD plus the lost volts. Or precisely, E equals to VR plus V subscript R. When I write capital R, I'm referring to the terminal PD. When I write small r, subscript small r, I'm referring to the lost volts. But remember, by Ohm's law, V equals to I times R. So for the terminal PD, V subscript R is going to be I times capital R. And for the lost volts, V subscript small r is going to be I times small r. Why is I the same? Because these capital R and small r are in series, so the current is the same. Therefore, it means E is going to be I capital R plus I small r. Or you can try to factor out this if you want. You put I outside, so E is going to be I into capital R plus R, because capital R plus small r is actually the total resistance in this circuit. And therefore, if I make I the subject, the current I is going to be EMF E over R plus R. So many times I'll be saying current is equal to the EMF over total resistance. Total current, or current through the battery, current from or through the battery, is always going to be equal to the EMF divided by the total resistance. The current which goes through the battery, or the current from the battery, is always going to be the EMF divided by the total resistance. This is going to be very important. And the PD, or the terminal PD, is the PD between the terminals of a cell when a current is being delivered. You will be asked to define terminal PD. The PD between the terminals of a cell, the most important point is this one here, when a current is being delivered. That is the most important thing. The PD between the terminals of a cell or the terminals of a battery when a current is being delivered is the terminal PD. And the PD, of course, between the terminals of a battery when there is no current, that was the EMF. So you should now know the difference between terminal PD and EMF. The PD between the terminals of a battery when the current is being delivered, that is terminal PD. And the PD between the terminals of a battery when there is no current will be the EMF. So when I make terminal PD the subject, of course, terminal PD will be EMF minus lost volts. Do not forget that the velocity volts is I times small r, and do not forget that the terminal PD is I times capital R, where capital R is the external resistance. A few things we need to note. The terminal PD is always less than the EMF when the power supply delivers a current. That is by conservation of energy. The PD across the terminals when there is a current cannot be cannot be greater than the power supply. So the terminal PD is always less than the EMF when the power supply delivers a current. So when the power supply is giving a current, the terminal PD is going to be less than the EMF. And the PD across the internal resistance, we shall always call it the lost volts. So whenever I talk about lost volts, I'm referring to the PD across the internal resistance, which accounts for the energy losses within the battery. So I'll be talking about it, I'll be calling it the lost volts. Also, I want you to note that if a cell has no internal resistance, like in many cases, you will be told that assuming no negligible internal resistance. So if a cell has no internal resistance, then the terminal PD is going to be equal to the EMF of the cell. So many times we shall be given a circuit, such as this one here, and they will tell us that assume that the cell has negligible internal resistance. So if the cell has negligible internal resistance and I connect a voltmeter across, the voltmeter will give me exactly the same value as the EMF. That means the PD across the fixed resistor will be the same as the EMF in that case. So if a cell has no internal resistance, then the terminal PD equals to the EMF of the cell, just as we mentioned with an open circuit. So it behaves as if it is an open, it will have almost the same effect as that of an open circuit, only that in this case, if it is delivering a current, then it is not an open circuit, it is a closed circuit. However, as long as it has no internal resistance, then the terminal PD and the EMF are going to be of the same value. So you recall the example I started with in this lesson of starting a car with its headlights switched on. So when we switch on the headlights, or when the headlights are switched on, a large current, which is many times approximately 100 amperes, is supplied to the starter motor by the battery. But this means there will then be a large PD across the internal resistance. Because the battery has some internal resistance and a large current of about 100 amperes applied to the starter motor, it means there will be a large PD across the internal resistance, because for the internal resistance it says 0.5 and then a current of 100 amperes is supplied. It means if I use Ohm's law, V equals to IR, this will be 0.5 times 100, which would be equal to around 50 volts. So this means there will be then a large PD across the internal resistance, which is going to be lost voltage. This is, let's say, approximately 50 volts. So it means the terminal PD, or the PD across the headlamps, will now drop. The PD across the headlamps will drop and the lights will be dim. So let's say the headlamps, or let's say the PD, the EMF of the battery used to light the headlamps is, say, 100 volts. But let's say the internal resistance of the battery is 0.5 volts. And a large current of 100 amperes is supplied to the starter to the starter motor by the battery. So the lost volts when the car is started is about 50 volts, which means if 50 volts is lost within the battery, it means what goes to the headlamps is going to be 100 minus 50, which will be 50 volts. So 50 volts to go to the headlamps. That means the PD across the headlamps is smaller than necessary, and therefore It means the terminal PD will drop and the lights will be dim. Of course, what determines the brightness of a lamp is the PD across the lamp. So if the PD across the lamp is reduced because of the internal resistance of the power supply, then the lamps or the lights will be dim to that effect. So in most cases, the internal resistance of a supply is assumed to be negligible. Like in most questions, we shall be assuming the internal resistance to be negligible so that the terminal PD across the load is equal to the EMF of the power supply. So whenever the terminal PD of the load is equal to the EMF of the power supply, many times we have assumed that the internal resistance is negligible or has been neglected. Warning. This is a very important thing to think about. It's like a warning. Remember, whenever whenever the circuit is complete, we expect the battery to supply or to deliver a current. Whenever the circuit is complete, we expect the battery to deliver or to supply a current. However, we are going to assume that there is negligible internal resistance within the battery so that there is no energy lost within between the terminals of the battery. Note that the maximum current that a power supply can deliver will be when its terminals are short-circuited by a wire of negligible resistance. That is, there is no external resistance. So in a circuit like this one here, where we have a power supply whose internal resistance is R, and we have a resistance R. Now here the battery is going to deliver a current, but if I remove this resistor here and I just put here a wire of resistance equal to 0, that is called short circuiting, causing a short circuit. Remember, current always takes the least resistive force. So it means when I join a wire or when I join the positive terminal to the negative terminal using a wire of negligible resistance, we say we have caused a short circuit. This is when the current is going to be maximum. Remember, current equals to the EMF divided by total resistance. So it means the current in this case is going to be the EMF divided by total resistance, which is 0 plus R. So here the current is going to be maximum. I is going to be maximum. So the maximum current that a power supply can deliver will be when its terminals are short-circuited, so that the external resistance is equal to 0. In this case, the terminal PD will be 0. So the PD across the external resistance here, V capital R, is going to be equal to 0. And this is very dangerous. So in this case, the terminal PD in this case will be 0. And in this case, the PD across the internal resistance will be equal to the EMF of the cell. Remember, the EMF we said is equal to the terminal PD plus the lost volts. So it means the EMF of the cell is equal to the lost volts. Now, this is very dangerous. You may find the battery could just end up exploding. If we short circuit a battery, we just join a wire of negligible resistance from the positive terminal of the battery to the negative terminal of the battery. And if there is negligible resistance between the positive and negative terminal of the battery for the external circuit, it means the external resistance is 0. The terminal PD is 0, which means the EMF of the battery is the same as the lost volts. This rapidly heats up the battery, which may end up causing the battery to explode. This is very dangerous, and this experiment should not be tried out as the wire gets very hot. This wire will get very hot and there is a danger of the battery exploding. Many times we might have seen short circuits and we might have seen wires catching fire because the current is going to be extremely large or it is going to be maximum. So the maximum current is delivered The maximum current that a power supply can deliver is when the external resistance is zero, or when the terminals are short-circuited by a wire of negligible resistance. Okay, so we are still trying to explore how we obtain internal resistance. So to obtain internal resistance, remember we have already seen that the EMF is equal to the lost the terminal P V capital R plus the lost volts V small r. And so the EMF, when I make the terminal PdV, I'll just call terminal PdV the subject. So V is going to be equal to the EMF minus V small r. But remember, V small r is current times internal resistance. So V is equal to EMF minus capital I times R. So I can easily investigate PD across a fixed resistor, or PD across a resistor, or PD across a power supply, and the current in the circuit using the voltmeter and the ammeter. So I can now come up with a graph. So to determine internal resistance, I will consider a circuit which incorporates the ammeter to measure for me the current, and the voltmeter to measure for me the terminal PD, that is the PD between the terminals of the cell of the power supply. Remember, if there is no current, the terminal PD is the EMF. If there is a current, the terminal PD is less than the EMF. By what amount? It is less than the EMF by the amount which is lost within the power supply. So I will obtain several values of maybe V. Of course, I have a variable resistor or a rheostat so that I can change the current flowing and the PD across the power supply. Or I can change the resistance, which causes a change in the value of V and the value of I. So I can have a value of V and the value of I, and then I have values of V and values of I, then I can plot a graph. So when you look at this equation here, you notice that the graph is going to be a straight line, but with a negative gradient, because if I plot a graph of V against I, this is going to be a straight line, which is going to have a negative gradient. This is going to be a straight line with a negative gradient if you look at this equation. And when I equals to 0, when I equals to 0, V is equal to E. So it means the y-intercept is going to be E, and the gradient is going to be equal to negative small r. Okay, so the circuit shown can be used to determine the internal resistance. So I can use this circuit to determine the internal resistance, as I've already explained. What is very important on this circuit is the position of the ammeter and the voltmeter. However, there's a variable resistor which helps us to vary the PD across the power supply and the current, so that we have different values of V and different values of I. So from V equals to E minus IR, we saw that EMF equals to the terminal PD plus the lost volts. So making V the subject, V is equal to EMF minus the lost volts. But the lost volts is the current times internal resistance R. So V equals to E minus IR. The graph of terminal PdV against the current I takes the shape which I've shown here, which I'm going to show here. So the y-intercept is equal to the EMF of the power supply, because when there's no current being supplied, the terminal PD is the EMF. And of course, the gradient is going to be equal to the negative internal resistance. I've just compared this with the y equals to mx plus c. If you rearrange, you have V equals to negative IR plus E. Then compare with the y equals to mx plus c. On the y-axis, you can plot V. On the x-axis, you have plotted I. So you notice that the gradient equals to negative R, and the y-intercept equals to the EMF. So the y-intercept is going to be the EMF of the power supply. That is when there is no current flowing, or when I is equal to 0. And the gradient is going to be the negative internal resistance. So the graph would take this shape. When I find the gradient, we have said the gradient or the slope. The slope is equal to negative r. But of course, you notice that the slope is negative. You will observe that the slope is going to have a negative gradient, or the gradient is going to be negative. Of course, it means the final answer will therefore be positive. When there is no current flowing, we already say that the terminal PD is equal to the EMF. The terminal PD is the PD across the terminals of the battery when the current is being delivered. When there is no current being delivered, the terminal PD is the EMF. As simple as that. I want you to note that a digital voltmeter has a very high resistance, that is approximately 117 ohms. So only a tiny current will pass through it. So the voltmeters we use in the laboratory, most of them have resistances of about 117 ohms. In comparison to the currents we use in the laboratory, which are very small currents, it means this resistance is very large. It can be considered to be infinite in comparison to the currents we use in the laboratory. So only a tiny current can pass through the voltmeter. After all, it is not designed to measure current. It is designed to just compare potential between 2 points and give a potential difference. So in this case, the lost volts due to the resistance will only be a tiny fraction of the EMF since negligible current goes through it. So if no current goes through the voltmeter, it means the lost volts due to its resistance is negligible. Since almost no current goes to the voltmeter, it implies that the lost volts due to the resistance of the voltmeter is going to be negligible. So we now know the relationship between internal resistance, terminal PD, and the EMF. And we now know how the graph looks like. And we now know what the slope of the graph looks like or gives us, and we know what the y-intercept equals to. These are the most important concepts you should think about, especially when you are going to do an exam of physics, paper 2 especially. Okay, so what is the effect of internal resistance on the power from a battery? Let's talk about the effect of internal resistance on the power from the battery. Let's consider a simple circuit such as this one, which incorporates a variable resistor, an ammeter, and a voltmeter. Note that the position of the voltmeter can also be here because we'll be giving the same thing. It is compared because the potential at this point is the same as the potential here. This is just a wire which would be of negligible resistance. The potential at this point is the same as the potential here. This could be just a wire of negligible resistance. So connecting the voltmeter either across the power supply or across the load, as long as the power supply is giving a current, whatever we are measuring is terminal PD, or that is PD outside the cell, as long as there is a current. So the position of the voltmeter should not be a problem as long as it is connected across a component. Okay, so the circuit shown here can be used to investigate the power transfer to an external load, such as this variable resistor here. So all we need is to find the readings of I, readings of the ammeter. So we shall find the readings of the ammeter here, and readings of the voltmeter, which is going to be the terminal PD across the load for different values of R. So of course we know that from our lesson, I think it was lesson 2 or lesson 3, no, lesson 3 I think, we saw that power delivered was equal to I times V, or it could be I squared times R, and so on and so forth. So the power delivered to the load is going to be given by a simple expression such as I times VR, where VR of course is the PD across the load, which can be I squared times R, where R is the resistance of the load. Now I'm going to assume that the EMF of the power supply is, let's say, 3 volts. And I'm going to assume that the internal resistance of the power supply is 2 ohms, even though 2 ohms is very big. So I'm going to vary the resistance of the load from 0 to 6 ohms because this is a variable resistor. Let me assume I vary the resistance of the load from 0 to 6 ohms. I'm trying to investigate the effect of internal resistance on the power supply. I mean, the effect of internal resistance on the power from the battery. So, I have assumed that the EMF of the battery is 3 volts, the internal resistance of the battery is 2 ohms, and the resistance of the variable resistor is going to be varied from 0 to 6 ohms. I'm going to start with R equals to 0. So suppose R is equal to 0, I'm using current equals the EMF over total resistance. Remember, there's an internal resistance of the battery which I've considered to be 2 ohms. So if I substitute 3 divided by 2, the current in that case is going to be 3 over 2 amperes. What is the power delivered in this case? Remember, power is equal to I squared times R, or power is equal to I times VR. But I'll use this because I have I and I have the resistance. I'm going to use power equals to I squared times R, where I is now 3 over 2, but R was 0. So the power delivered is going to be equal to 0. So when the load resistance is 0, the power delivered is 0. Okay, let me check what happens if the resistance is 2 ohms. Remember I said the resistance of capital R varies from 0 to 6 ohms. Suppose the resistance of capital R is now 2 ohms. I've skipped 1. You can try 1. So it means total resistance is going to be 2 plus 2. Remember, I have to remember to add the internal resistance because these are in series. If this is 2, there's internal resistance there which is 2. So it means the current is going to be equal to 3 divided by 4 amperes. And using the same formula, power delivered equals to I squared times R. The current is 3 over 4, but squared times the load resistance, which is capital R, which is 2. It is giving me 1.125 watts. So you notice that when the resistance is 0, the power was 0. When the resistance is 2 ohms, the power is 1.125. Remember, 2 ohms was also the internal resistance. Okay, let's try to increase beyond 2. That is beyond the value of R to be greater than. So here we have R equals small r. It is 1.125. Let's think of a situation where R is greater than small r. Maybe let's check 4 ohms. So if we use 4 ohms, the current will be EMF over total resistance, which is 3 over 6 amperes. That is the current. When I substitute in power equals to I squared R, the power will be 3 over 6 squared times 4. And this is giving me 1.0 watts. You notice that this value here is less than the first one. The power, when the resistance is greater than the internal resistance, the power is less than that value when the resistance is equal to the internal resistance. Maybe that's an error. Let us check for R equals to, again, R is greater than small r, but let's say it is equal to 6. So for R equals to 6, total resistance is going to be 6 plus 2. Remember to add the internal resistance because they're in series. So it means the current is going to be 3 over 8. When I try to substitute in the equation power is equal to I squared over R, I squared R, I got 0.84. So it's like it increases from 0 to a maximum value when capital R is equal to small r, and then it decreases. What is this telling us? It appears as if power delivered by the battery is maximum when the resistance of the load or the external resistance is equal to the internal resistance. A battery supplies maximum power when the internal resistance is equal to the load resistance, or when the external resistance is equal to the load resistance. So in a nutshell, what we have been saying is that we have observed that the power is greatest when capital R is equal to small r. It was equal to 2 ohms. Hence, we conclude by saying that a battery delivers maximum power to a circuit when the load resistance R of the circuit is equal to the internal resistance small r. A battery delivers maximum power to a circuit when the load resistance of the circuit is equal to the internal resistance of the battery. So we can even sketch a graph therefore. Of course, the variation may not be linear. If you recall, if you try to calculate, the variation may not be linear. But we know that it is maximum. The graph of power against the load resistance is going to be maximum at internal resistance, when load resistance equals to the internal resistance. So if I sketch a graph of power against the load resistance, I expect to get a graph of this nature, where I have maximum power when the load resistance equals to the current. So here the load resistance R is equal to the internal resistance. When the load resistance equals to the internal resistance, the power is maximum. We saw when R was equal to 0, the power was equal to 0. We saw that when R was equal to small r equals to 2, the power was actually maximum. And when R is greater than small r, or it is greater than 2, so that the power now starts decreasing. We can even check what happens when R equals to infinity. Of course, when R equals to infinity, it means the current equals to 0, because remember, current is equal to the EMF over total resistance. So it means when R equals to infinity, the current tends to 0. And if I tends to 0 from power equals to I squared R, it means the power tends to 0. That's why this graph may touch the x-axis with time, even though we cannot reach infinity. So in most cases, I always encourage my students to just sketch this graph in such a way that it doesn't touch the x-axis on the other side, but tends towards 0, because we may not reach infinity in most cases. So this would be power maximum, and here we have internal resistance. So this is a graph of power delivered against the load resistance. The load resistance R. So here R is equal to small r. When R equals to small r, the power is maximum. So many times I encourage my students not to make this graph touch the x-axis, but even if it touches the x-axis, we are interested in the fact that a battery delivers maximum power to a circuit when the load resistance equals to the internal resistance R of the battery. That is the most important concept in lesson 5. Okay, so here I have a summary for us to match. Summary. Match these phrases about EMF. Potential difference across a power supply. The EMF of a cell, the EMF of a cell on a graph. Voltage drop between the source and the load. The internal resistance of a cell on a graph. Maybe I can just sketch for you a graph here. A graph of V terminal PD against current was a graph which was like this. And this was the EMF. The gradient was the internal resistance of a cell was the gradient of a voltage graph. So this one goes to the terminal resistance of a cell on a graph is the gradient of the voltage current graph. Then voltage drop between the source and the load, that is the lost volts. Potential difference across a power supply, that is PD across a power supply when there is a current, that is the terminal PD. And the EMF of a cell on a graph, that is the y-intercept. I think that is the correct match. Terminal voltage or terminal PD is the PD across a power supply as long as there is a current being delivered. Then lost volts, that is the voltage drop difference, because lost volts is equal to the EMF minus the PD across the component outside, or across the terminal PD minus the terminal PD. So this is a drop in voltage. That's why we call it lost volts. Okay, so I think that is a good match to summarize that part. Let's now do a few examples. A high resistance voltmeter reads 13 volts when it is connected across the terminals of a battery. The e.m.f, so when it is connected across the terminals of a battery, it reads 13 volts. The voltmeter reading drops to 12. So this is e.m.f. There was no current. So it drops to 12 when the battery delivers a current. So now this is going to be the terminal PDV. So when I write V, many times I will refer to terminal PD. It delivers a current of 3 amperes. State the EMF of the battery. Calculate the PD across the internal resistance, that's the lost volts, when the battery is connected to the lamp. Calculate the internal resistance of the battery. So when there is no current, the reading of the voltmeter is the EMF. And when there is a current, the reading of the voltmeter is the terminal PD. So the lost volts is the difference between those two. So that is very simple. So in our solution, we know that the EMF is going to be 13 volts since this is the voltmeter reading when the battery is not delivering a current. Then using the fact that lost volts equals to the EMF minus the terminal PD, I will just substitute and I get 1.0 volts. That is the lost volts. But remember, the lost volts is equal to the current times the internal resistance. So I will just equate to 1.0 volts to IR. So using VR is equal to IR, then R is the lost volts divided by current. So this gives us 0.33 ohms. Five volts PD is measured across a power supply with internal resistance 10 ohms. That is less likely because that would be a very big resistance. An 8 ampere current flows. What is the EMF of the power supply? So we know that EMF, when I write E, I will be referring to EMF equals to the terminal PD plus the lost volts. So 5 volt PD is measured across a power supply with internal resistance 10 ohms. So small r is 10 ohms. This 5 volts is measured across a power supply with internal resistance 10 ohms. An 8 ampere current flows. So the current flowing is 8 amperes. What is the EMF of the supply? So the easiest way to think about this is maybe to draw a simple sketch, even though it's not necessary. So they have measured the PD across the terminals to be 5 volts. And remember, this is if there is a current flowing, then what is measured is the terminal PD. So this is V. V is 5 volts. And the current of 8 amperes being supplied. So the EMF is equal to the terminal PD plus the lost volts, which is I times small r. So the EMF is going to be 5 plus the current is 8 times the internal resistance, which is 10, which gives us 85 volts. A single cell of EMF 1.5 volts is connected across 0.3 ohms. The current in the circuit is 2.5 amperes. Calculate the terminal PD and explain why it is not equal to the EMF of the cell. So a single cell has EMF 1.5 volts. It's connected across a 0.3 ohm resistor. The current in the circuit is 2.5. So the terminal PD is going to be the current times the external resistance, which is 2.5 times 0.3. 2.5 times 0.3. So this is going to be 0.75 volts. So that is the terminal PD. Explain why it is not equal to the EMF of the cell. So the cell has some internal resistance. So maybe the cell has internal resistance. So the internal resistance accounts for the lost volts. So which accounts? The cell has internal resistance which accounts for lost volts. Show that the internal resistance R of the cell is 0.3 ohms. So of course the the lost volts is going to be 1.5, that is the EMF minus the terminal PD, which is 0.75 volts. That is the lost volts. But the lost volts 0.75 is equal to the current, which is 0.2.5 times the internal resistance small r. So 0.75 divided by 2.5, this implies that small r is equal to 0.3 ohms. That is direct. It is suggested that the power dissipated in the external resistor is maximum when its resistance R is equal to the internal resistance small r of the cell. That is true. Calculate the power dissipated when R equals to small r. So the current, remember, is 2 point. When R is equal to small r, total resistance or current is equal to the EMF, which is 1.5, over total resistance, which is 0.3 plus 0.3, which is going to be 0.6. So the current is going to be 1.5 divided by 0.6, or the current is 2.5 amperes. So that is the current. And then the power dissipated is going to be equal to I squared times R, which is going to be 2.5 squared times R, which is 0.3. So that's squared times 0.3. So this is approximately 1.9 watts. Show that the power dissipated when R equals 0.5 and R equals 0.2 is less than the power that dissipated when R equals to, okay. So for R equals 0.5 ohms, the current flowing is going to be equal to EMF, which is 1.5 over total resistance, which is 0.3 plus 0.5, which is 1.5 divided by 0.8. The current flowing here is going to be 1.875. The power is going to be equal to I squared R, which is 1.875 squared times 0.5. So this is giving me 1.8 watts. That is for 0.5. Then for 0.2, current is going to be the EMF 1.5 over total resistance, which is 0.3 plus 0.2. 0.3 is the internal resistance, then plus 0.2 because they're in series. So 1.5 divided by 0.5. So this is going to be 3 amperes. And the power dissipated, is going to be 3 squared times 0.2, which is equal to 1.8 watts. So in both cases, of course, this was 1.75, I think, but I rounded off to 1.8, and this is 1.8 watts. So in both cases, the values are less than 1.9. They are less than the power at when R is equal to the internal resistance. So we have just tried to verify this. that a battery delivers maximum power when when the load resistance is equal to the internal resistance, and that is very, very important. Okay. Okay, so explain what is meant by internal resistance of a cell. So we know that internal resistance is the resistance between the terminals of a battery, which accounts for the loss of energy within the battery or inside the battery or inside the cell for that matter. When a dry cell is connected in series with a resistor of 2 ohms, there is a current of 0.625 amperes. So remember the current is equal to the EMF divided by the total resistance. RT is equal to total resistance. So it means the EMF is going to be the current times the total resistance. So we have a resistance, let the internal resistance be small r. If a second resistor of 2 ohms is put in series with the first one, the current falls to 0.341 amperes. Calculate the internal resistance of the cell. So let the internal resistance be small r. So for the first case, the EMF is not known. Let's say E equals to the current, which is 0.625. The internal resistance is going to be, because we have the 2 ohms is in series with the internal resistance of the battery, so this will be 2 plus small r. Let this be one equation. Then for the second one, we have now 3 resistors in series. We have 2 ohms in series with the second one and in series with the internal resistance. So the second equation is going to be EMF equals to, the current drops to 0.341. So it is 0.341 into 2 for the first resistor plus 2 for the second resistor plus the internal resistance, that is the total resistance. So I'm just going to equate the two equations where I will say that 0.625 into 2 plus r should be equal to 0.341 into 4 plus r. So I have just equated the two equations. Opening the brackets, I'm opening the brackets at the same time collecting like terms. I hope you are good mathematicians than me. So I'll say 0.625 r minus 0.341 r. I've collected like terms for r to the left. Then to the right, I have 0.341 times 4 minus 0.625 times 2. So I've just pressed my calculator. 0.625 minus 0.341. So I have 0.284 r being equal to, on the right hand side I have 0.341 times 4 minus 0.625 times 2. On the right hand side I have 0.114. Then I will divide by 0.284. So R is going to be equal to 0.40 ohms. So the internal resistance is going to be 0.40 ohms. That is just algebra. Then the EMF, I will just substitute in one of the equations. Maybe I will substitute in the first equation. The EMF is equal to 0.625 into 2 plus 0.40. So we have 2.4 times 0.625, which gives us 1.5 volts. Then a car battery needs to supply a current of 200 amperes to turn over the starter motor. Explain why a battery made of a series of dry cells would not be suitable for a car battery. So a series of dry cells implies that the internal resistance is bigger, and if the current is 200 amperes, It means there will be a large PD across the internal resistance of the cells, which reduces the PD across the starter motor, so it will not be good enough. So the internal resistance of the batteries of the cells reduces the PD across the motor. So there's an internal resistance which reduces the PD across the motor, which affects starting the motor. State what is meant by the term EMF. Like we have said, we can define EMF in terms of energy transferred by this power supply to a unit charge, or energy transferred from chemical to electrical per unit charge. That is for a cell. Energy transferred from chemical to electrical per unit charge. A student connects a high resistance voltmeter across the terminals of a battery and observes a reading of 8.94 volts. He then connects 12 ohm resistor, so it means this is going to be the EMF. A student connects a high resistance voltmeter across the terminals of a battery and observes 8.94 volts, so that is going to be the EMF. He then connects a 12 ohm resistor across the terminals and finds that the PD falls to 8.4. So this is going to be the terminal PDV. Explain why the measured voltage falls. So the fall in voltage is the lost volts. So the lost volts is due to internal resistance. Internal resistance of the battery. Capture the current in the circuit. So if I have the PD and the resistance, so I will simply say V equals to I times R, which means the current is going to be the terminal PD, which is 8.4 divided by 12. So 8.4 divided by 12, this is going to be 0.7. Then capture the internal resistance of the cell. So we first get the lost volts. The lost volts is equal to 8.94 minus 8.4, which is equal to 0.54? So the lost volts is 0.54, but we want the internal resistance. Remember, lost volts is equal to I times R. The same current flows. So the lost volts is 0.54, and the current, the current was 0.70 amperes, not volts. So this means this is going to be 0.54. So R is going to be 0.54 divided by the current, which is 0.70. The current is 0.70 amperes, not volts. So divide by 0.7. So this gives us 0.77 ohms. Set any assumption you made in your calculation. So which assumption can we make here? So we can assume that the resistance of the connecting wires is negligible in the first place. Also, we can assume that the internal resistance remains constant. So we are assuming that R internal resistance remains constant. But remember, the resistance also can be affected by temperature. If the power supply warms up, this could affect the internal resistance. But we are assuming internal resistance remains constant. Number two, we are neglecting the resistance of the connecting wires. and so on and so forth. So those are some of the assumptions that I can think about. You can think about many more. Let's also talk about combination of cells. So, of course, we know that energy-consuming devices that form the loads of electric circuits are designed to draw the proper current from their operation when a specific PD exists across their terminals. So, devices are designed so as to pull out or to take away a specific amount of current which is needed for their operation from the terminals of the power supply. For example, a bulb which is designed for use in a 3 volts electric system will draw an excess current and burn out if you put it across 6 volts. So, if a bulb is designed to use 3 volts, if you put it across 6 volts, it may draw excess current and just blow out. Yet on the other hand, a bulb that is intended for use in 6 volt system would not draw sufficient current at 3 volts. So if a bulb needs 6 volts and you connect it across 6 volts, then it may not, if a bulb needs 6 volts and you connect it across 3 volts, it may not draw enough, or sufficient current for it to work as required. So the electrochemical cells are the sources of the EMF in most cases, and each cell gives a certain amount of energy to the circuit for each column of charge that is moved. So if we have cells, these ones have chemicals in them, and each of these cells is expected to give a certain amount of energy to every charge which passes through, so that the chemical energy is converted to electrical energy. Thus, it is necessary to combine in order to provide either the proper EMF or the adequate source of current. So sometimes we may need to combine cells either in series or in parallel depending on what we need for our circuit. So if I have a group of cells connected together, they will constitute what we call a battery. That's why even when you look at the symbol for a battery, it is actually like this. That is how we represented a battery. It's like showing how many cells assembled together to form what we call a battery. So the EMF of a battery depends on the EMF of the individual cells and the way in which they are connected. So we can combine cells to give a very large EMF, or we can combine cells to give a very small EMF. Therefore, the EMF of a cell is depending on how the individual cells are combined, or it depends on the EMF of the individual cells and their orientation or how they are really connected to each other. So let's first look at cells combined in series. Of course, we know what we mean by series, that is end by end, side by side. One cell is joined to another cell. So in this case, for example, we notice that the negative and the positive terminals of each cells are linked up to form a series combination of cells. When cells are combined in series, remember if each cell has internal resistance R, let's say R1, R2, and R3, assuming they are not identical, it means their total internal resistance adds up. So if cells are joined in series, the effect or the problem is that total internal resistance becomes bigger, which means the lost volts is going to be big, and that means the terminal PD becomes smaller. So when cells are joined in series or end to end, the same current passes through these cells. The same current is going through these cells, or the same current must flow through each of the cells, but their EMFs adds up. So a charge which passes through cell of cell E1 gains energy from E1, it gains energy from E2, it gains energy from E3. That means it has more energy. Therefore, the EMF adds up. So for cells in series, total EMF is the sum of the individual EMFs. And of course, total internal resistance is also the sum of the individual internal resistances. For the cells in series, we sum up the EMFs, we sum up the internal resistances. And if these cells were identical so that each has EMF E and each has internal resistance small r, in that case it means total EMF is going to be 3E and total internal resistance is going to be 3R. So if each cell has internal resistance small r and EMF E, it means the total EMF is going to be 3E, and the total internal resistance is going to be 3R. For example, let's think of a simple situation where we have several cells combined in different ways. In A, we have this cell is joined in such a way that the positive and the negative terminals are linked. So we have positive, negative, positive, negative. So it means if this is each of these is 3 volts, I mean 1.5 volts, 1.5 volts. So it means here we shall just sum them up because they are arranged in such a way that the positive is linked to the negative, so they are combined in the correct direction. So the EMF here is going to be 3.0 volts. If cells are combined in this nature here, we have a positive joined to negative, positive joined to negative, and so on and so forth. So we have 1.5 plus 1.5 plus 1.5. This gives us 4.5. I'm assuming that a normal cell each has an EMF of 1.5 volts. However, if cells are combined in this nature, notice that the positive terminal is joined to a positive terminal. And here we have a negative terminal joined to a negative terminal. So you can consider, because current flows from positive to negative. So the current from, say, this cell is in this direction. The current from this cell is in this direction, but the current from this cell is in the opposite direction. So one cell is in the opposite direction. The current from it is in the opposite direction. So here the total EMF is going to be 1.5 minus 1.5 plus 1.5, which gives us 1.5. So when you look at the orientation of these cells, you should be able to identify the fact that the total PD is going to be 1.5 volts. So look at the combination of the cells very carefully. I will add one example here. Let's have cells 1, 2, 3, 4, 5, 6, 7, 8. So let's have these cells, 8 cells joined like this. So for this one, the current is in this direction because current is from positive to negative. Current is in that direction. Current is in that direction. This one, current is in the opposite direction. It is in that direction, opposite direction, opposite direction, in that direction. So you notice we have 1, 2, 3, 4, 5 to the right hand side. That is 5 times 1.5 plus negative 1, 2, 3, 3 to the left. So it is 3 times 1.5. So the total EMF or the total PD or total EMF is going to be, I think this is 7.5 minus 4.5, which gives us 3 volts. So the effective EMF is going to be 3 volts. So you should be very careful with the direction of the current from the cells when you are combining them. So that is for cells in series. Let's talk about cells in parallel. So if we have cells in parallel like this, it would be good to look at this combination if we have already mentioned Kirchhoff's laws, but we shall still talk about it regardless. So this is a parallel combination where cells are joined to form a common link, so they have a common point. So the potential for this cell is the same as the potential here, is the same as the potential, which is the same as the potential here. Then the potential for this point here, the negative terminal, is the same as the potential here, is the same as the potential here, is the same as the potential here. What does that mean? It's like if I connect a voltmeter across any 2 points between the cells, it will always give the same reading. When I put a voltmeter here, or here, or here, or here, whatever point I put the voltmeter, it will always give the same reading. What does that imply? When cells are joined in parallel, the effective EMF from them is just equivalent to the EMF of just one cell. So in a parallel combination of cells, all negative terminals are connected together, and the common terminal formed is connected to the external circuit. The positive terminals are also connected together, and this common terminal formed is also connected to another the side of the circuit. So if this cell, the combination is now connected to maybe a battery or a bulb, not a battery. So they are forming a common terminal, and then this is connected to a battery. So the common positive terminals are also connected together, and this common point is connected to the other side of the circuit. So for identical cells, total effective EMF is equal to the EMF of just one cell. So if these cells are identical and each has EMF E, then the effective EMF across this bulb is just going to be the EMF of just one cell. And of course, total resistance, because these are going to behave as if they are resistors in parallel. And for resistors in parallel, we know that total resistance 1 over R total is equal to 1 over R plus 1 over R plus 1 over R. So for these cells in parallel, total resistance 1 over R total is going to be equal to 3 over R. When I get the reciprocal, R total becomes R divided by 3. So it's like a total resistance in series becomes 1 over 3 times R. This is an advantage, of course. This is an advantage. If we have our cells in parallel, the effective internal resistance becomes smaller, which means the lost volts is going to be smaller. The lost volts is going to be smaller. But of course, we shall see this using Kirchhoff's laws. If the cells have different EMFs, we cannot use this analogy that I've just considered. Then we can only get the effective EMF using Kirchhoff's laws. So if these cells are not identical, then we can get the effective EMF using Kirchhoff's laws, which we are going to explore in lesson 6. Okay, that is a combination of cells. Let me give a simple example here. So I'll explain why two identical cells, EMF E and internal resistance R, connected in series, deliver more current than when in parallel. So we have two identical cells connected in series, and we are saying they are delivering more current than when they are connected in parallel. Let's see why that is possible. Of course, we know that if they are in series, number one, the total effective EMF is twice R, total internal resistance is 2R. And if they are connected to an external resistor R, then total resistance is going to be 2R plus capital R. So if they are connected to an external resistor, whose resistance is capital R, then a current flows, of course, and from EMF is equal to total current times total resistance. Remember, the EMF is twice E. Total resistance, R total, is going to be 2R plus capital R. That is total resistance. So it means total resistance is going to be equal to R plus 2R. So twice E equals to IS, where IS is standing for the current if it is in series. And when I make IS the subject, this is what I have. Twice E over R plus 2R. Let's think of a situation when they are in parallel. Suppose they are joined in parallel. If they are joined in parallel, remember total EMF is just the EMF of just one. So effective EMF is just the EMF of one cell. If they are joined in parallel, total internal resistance is half of the resistance of just one. So that is total effective internal resistance. That is the effective internal resistance. And when the cells are now joined to an external circuit, it means the total resistance in the circuit is the resistance of the total internal resistance plus the external resistance, because it would be like having two cells in parallel forming a circuit, and then this is joined in series with a resistor R and something like that. So these two form a resistor whose resistance is R over 2, which is in series with an external resistor whose resistances are. Now, people will say, can't we say that these three are in parallel? That is wrong physics. So the two cells form an internal resistance, which is a half R, which internal resistance is in series with the external resistor. So it's like one cell whose resistance is a half R, but then that resistance is in series with an external resistor of resistance R. So it means total resistance here is going to be capital R plus R divided by 2. So using the expression E equals to IT times RT, then E is going to be IP, where P stands for parallel, into R plus R over 2. When I make IP the subject, it is going to be E over E plus R over 2. When you compare this expression here and this one here, you're going to notice that IS is bigger than IP. Maybe I can try to modify this for some people. This is going to be E divided by twice R plus R divided by 2. Then the 2 goes up. So this becomes twice E divided by 2R plus R. So when you compare this equation here with the first one, you notice that the denominator in the second one is going to be bigger because normally the internal resistance is smaller. So even if it is doubled, it means R plus 2R is less than 2R plus R. So which means IP is going to be bigger than, IS is going to be greater than IP in that case, because the denominator for IS is smaller than the denominator for IP. Hence, we just conclude by saying that IS is bigger than IP. So cells in series will deliver more current than when in parallel. If cells are used in series, they are going to deliver more current than when they are in parallel. The disadvantage is only going to be more lost volts when used in series, but they will deliver more current than when in parallel. They will also, of course, dry out. They will get used up very fast if used in series. But of course, those in parallel would last longer. That's why those in parallel are used in power banks. Okay. So I want you to note that the cells in a power bank, for example, are all connected in parallel. There's a reason as to why. Even though the cells in a series deliver more current than the cells in parallel, those ones used in power banks are always in parallel instead of being in series. Because for a power bank, we don't want to deliver more current but we want the power bank or the power to last longer. So parallel connection makes electrical energy last longer. The cells themselves have their internal resistance. So if they are connected in a series, some energy will be lost. Some energy will be lost in overcoming the internal resistance since its effect is high when in series than when in parallel. So we have seen the disadvantage of having cells in series. The total internal resistance becomes bigger, so we expect more lost volts in series. The advantage is that they will deliver more current. Then for parallel, they may not deliver more current or they don't deliver a lot of current. However, the total internal resistance becomes smaller, the lost volts become smaller, and also the parallel connection makes the energy to last for a longer period of time. Okay. So those are the concepts we were supposed to explore in lesson 2. So what remains is just further examples to make us confident with this unit of electricity, especially the first unit. You can always pause the video and you try to first to solve. I will not solve all the questions. Some of them I'll just give hints, but most of them are just emphasizing the same concepts we have been dealing with right from lesson 1. Okay, further examples. Two cells each of e.m.f are 1.5 volts and negligible internal resistance are connected across resistors 2 ohms, 3 ohms. Calculate the total current in the circuit. So remember, current equals the EMF over total resistance, that is total current. Total resistance, these ones are in parallel. We saw that for resistance in parallel, if there are only two, because it has no internal resistance, so this will be product divided by the sum. So total resistance is equal to 6 divided by 5. 6 divided by 5, which is 1.2. So total resistance is 1.2. So, and then total EMF, because they're in series, total EMF is 3 volts because they're in series. So this is going to be 3 volts divided by 1.2, which makes this to be correct. You can verify. Then the current that passes through the 2 ohm resistor. So because these are in parallel and there is no internal resistance for the battery, so it means the PD across each of them is still 3 volts. So here I'll just say current is equal to V over R, which is going to be 3 divided by 2. And here the current is going to be V over R, which is 3 divided by 3. The power dissipated in the 3 ohm resistor, power is going to be I squared times R, which is going to be the current in a 3 ohms is 1 squared times 3, which gives you 3 watts. So those are very easy questions. Two cells each have an EMF of 1.5 volts and internal resistance 2 ohms. They are connected in series and in parallel. Find the current in each case. Just to recall that current equals the EMF divided by total resistance. That is total current. Here the EMF, the batteries are in series, so the EMF is 3 volts. Total resistance, the resistors are in series, so we have 2 plus 2 plus 1, which is 5. So that gives us a 0.6. Then in B, they are in parallel. So if they are in parallel and we want to find the current, okay, so current still is equal to the EMF over total resistance. However, here the batteries are in parallel. So the effective EMF is automatically 1.0 volts, so the EMF is 1.5 volts. But the total resistance, we can't take these 3 resistors to be in parallel, not at all. The internal resistances are in parallel, which gives us, so resistance for this, or internal resistance is going to be 2 times 2 over 2 times 2, which gives us 4 over 4, which is 1 ohm. But this 1 ohm is in series with the 1 ohm, so total resistance becomes 2. R total will be the effective internal resistance, which is 1, plus the external resistance, because it will be like one cell whose internal resistance is 1 ohm, but in series with 1 ohm. So if I redraw this circuit, I'll have one cell like this one joined to a resistor of 1 ohm. So this is 1 ohm. This is one cell of 1.5 volts because it is the effective one. And its internal resistance is going to be 1 ohm after combining those two. So this gives us 1.5 divided by 2, which is, I think, 0.75 amperes. I think those are the only complex questions for us. Three identical cells, each of EMF 1.5, are connected in series to a lamp of 15 ohms. The current in the circuit is 0.27 amperes. Calculate the internal resistance of each cell. So there are 3 and they are identical. They are connected in series to a 15 ohm lamp. The current in the circuit is 0.27 amperes. Calculate the internal resistance of each cell. Maybe I can just sketch this 1, 2, 3. So they are connected in series with the lamp of 15 ohms. So let each have resistance R. So because they are identical, effective EMF is going to be 3 times 1.5, which is 4.5 volts. That is effective EMF. Effective internal resistance, R total, is going to be 3R. The current in the circuit is 0.27. Remember, current is equal to the EMF divided by total resistance. So, and remember, total resistance is 3R. Total resistance is going to be 3R plus 15. So I will say that making R at T the subject, so I will say that 3R plus 15 is equal to the EMF, which EMF is 4.5 divided by the current, which is 0.27. So I'll say 4.5 divided by 0.27. Then I subtract 15. Then I divide by 3. Calculate the internal resistance of each cell. So the internal resistance of each cell is approximately 0.56. Let me repeat this. 3 identical cells, each of EMF 1.5, are connected in series to a lamp of 15 ohms. So they are connected in series to a lamp of 15 ohms, so 1.5 times 3. So the effective EMF is 3 volts. And calculate the internal resistance of each cell. So if they're in series, total internal resistance is going to be R plus R plus R plus 15, that is 3. 3R plus 15, that is total resistance. So current equals the EMF, which is 4.5, divided by total resistance, which is divided by total resistance, which is 3R plus 15. So 4.5 divided by 0.27, 16, minus 15. Then divide by 3. So this is not correct. I think that student got that wrong. So this answer is going to be 0.56 ohms. Okay, so I think you can now, this is supposed to be 0.56 ohms. I expect that a serious student at this point should now be able to pause the video at every point and work out all these questions just to gain confidence. So you can pause the video and try question. This is supposed to be question number 4. Calculate the maximum current it can deliver under what circumstance does it deliver maximum current. Of course, we said a battery delivers maximum current when it is short-circuited. In other words, when the external resistance is equal to 0. Calculate also the maximum power it can deliver to an external load. We said the maximum power is delivered when the internal resistance equals to the load resistance. A battery of EMF 5 volts and internal resistance 2 ohms is connected to an 8 ohm resistor. Draw a circuit diagram and calculate the current in the circuit. You should be able to draw the diagram and try to see if that answer is correct. Not all these answers might be correct, because I recorded them from my student's suggestion. Okay, so you should be able to answer those questions. Pause the video and try to solve and see if you can come up with these answers where possible, or you may get varying answers. Remember, lost volts EMF is equal to terminal PD plus the lost volts. Remember, combination of resistors in series and combination of resistors in parallel. You should be able to answer this question. In the circuit, the battery has negligible internal resistance. Find the ammeter and the voltmeter reading. Of course, when we talk about the ammeter is connected to the battery, so we want total current in the circuit. Total current is the EMF divided by total resistance. Then the reading of the voltmeter is connected across 6 ohms. So you want the PD across 6 ohms, which means you need to find the current through 6 ohms times the resistance, which is 6 ohms. So you need to find the current which goes to 6 ohms. And of course, maybe this may not be very easy for some students, especially those who are not very good at GCSE. I'll try to solve this. So we have this resistor and this one are in parallel because they have two common points. So these ones are in parallel, the resultant is in series with the 2 ohms. So these ones are in parallel, so resistance in parallel is 6 times 12 over 6 plus 12, which gives us 6 times 12 divided by 18. So this is 4 ohms. 4 ohms is in series with 2 ohms, so that means total resistance is going to be 4 plus 2, which gives us 6 ohms. So the total current, I total is equal to EMF divided by total resistance, which will be 12 volts divided by 6. So it means total current is going to be 2 amperes. So total current is 2 amperes. And we want now to find the reading of the voltmeter. So the 2 amperes flows up to this junction and it divides. It divides, part of it goes to the 12 ohms and part of it goes to the 6 ohms. Of course, current is divided in the ratio of the resistances. There are two ways of getting this. Alternatively, remember the PD across 12 ohms is the same as the PD across 6 ohms. So I can just first of all find the PD across 2 ohms, which is going to be equal to, I'm using V equals to IR because the total current of 2 amperes flows through 2 ohms. So the PD across 2 ohms is going to be 2 times 2, which is equal to 4 volts. The current through 2 ohms is 2 amperes, but the 2 amperes is divided into the 12 ohms and the 6 ohms. Remember the same PD, this is the PD across 2 ohms, so I will also find the PD across the parallel combination. PD across the parallel combination. So from the power supply of 12 volts, I'll remove the PD across 2 ohms, and the balance, which is 80 volts, is the PD across the parallel combination. If I have the PD across the parallel combination, it means the PD across 12 ohms is the same as the PD across 6 ohms because they're in parallel, which is equal to 80 volts. So that means the reading of the voltmeter is simply going to be 80 volts. That is the easiest way without even trying to find the current which goes through each. I can find the PD across the resistor which is in series with the battery directly, then I subtract it from the EMF and I get the balance. It will be the PD outside, the PD on the parallel combination. So the answer is going to be 80 volts. Okay, so you can think about such questions. Okay, so I think this is going to be my last example to solve for some of you, because I can't solve all the examples. My students should also solve the questions. You should always pause the video and you try to work out. In the figure, X is an accumulator, EMF 24 volts, and having internal resistance of 1 ohm. So there is a resistance here of 1 ohm. There's a resistance there of 1 ohm. So calculate the effective resistance. So the effective resistance, when you study Kirchhoff's laws, you'll have easier methods of finding effective resistance. But before Kirchhoff's laws, we can still find effective resistance. So 1, 2, 3 resistors have two common points, 1 and 2. So they're in parallel. So I can get the effective resistance from 1 over resistance in parallel being equal to 1 over 2 plus 1 over 3 plus 1 over 6. LCM is 6. So that is 3 plus 2 plus 1, which becomes 7. I mean 6 over 6, which is equal to 1 ohm. So for the three resistors, they are forming one resistor whose resistance is 1 ohm, and it is in series with the 5. So it means we have these ones at the bottom, we have 5 plus 1, which is 6. So at the bottom, we have 6 ohms in total. These two are also in series. They are forming a resistor of resistance 9 ohms. So I have a simplified circuit like this one here. So here I have 6 ohms, I have 9 ohms, I have 7 ohms, and I have 1 ohm for the internal resistance. So these are also in parallel again. I'll have, since they are only 12, say 9 times 6 over 9 plus 6 to give us the total resistance there. So total resistance there is 9 times 6 divided by 9 plus 6. So the resistors in parallel are giving us a resistance of 3.6 ohms. 3.6 is in series with the 7. Or in other words, we have a resistor, we have a new circuit which is somehow like this, where this is 3.6 ohms, this is 7 ohms, and the internal resistance here is 1 ohm. So we now have three resistors in series. So total resistance is going to be 3.6 plus 7 plus 1, which gives us 11.6 ohms. If you can arrive at such a resistance, then you are good enough to go. A very good student does not show all this. A very good student just picks up a calculator and presses it. Using the combinations in the head, a product over the sum where possible, reciprocals, power to the negative of 1 where possible, the student can find the effective resistance very easily. Then total current. So total current is equal to the EMF divided by total resistance. So the EMF is 24, total resistance is 11.6, which I think should be able to give us about 2.1 amperes. So the rest you can just pause the video and try to work through. This is an extension question, so if you're able to solve this question, then you're a very powerful student. You can also try this one, question 10. You can also try questions 11, 12, and 13. You should also be able to try questions 15 and 14. Please pause the video and try to work out. I can't leave you to work out for the rest of the video, so I have to move very fast. I just show you the questions, so you pause the video and you try to solve. I have more self-check questions, but these are just for your practice. Self-check 1. This is a classroom activity. You can just press the calculator. My students are supposed to do this in the class without my guidance. Self-check is continuing. Self-check continues. Question 8. Self-check continues to question 9. Calculate the current at each points A to E in the above circuit. So A, B, and E are in series with the battery, so the current is the same. Maybe let me solve this one. The current in A is going to be the same as the current in B, which will be the same as the current in E because they are just in series with the battery. And this is going to be the same as the total current. So we are trying to find total current. Finding total resistance first. These ones are in parallel. Resistance in parallel is 300 times 60 over 300 plus 60, which gives us 300 times 60 divided by 300 plus 60. So this one is 50. Resistance in parallel. So 50 is in series with 50. So total resistance is going to be 100 ohms. So to find total current, which is the current through A, B, and E, total current is going to be the e.m.f divided by total resistance, assuming the internal resistance is negligible. So this will be 600 divided by 100. So the total current is going to be equal to 6 amperes. So it means I in A, which is the same as I through B, which is the same as I through E, is 6 amperes. Then we have C and D. C and D. So to find current through C and D, I can just find the PD across 300 ohms, which is the same as the PD across 60 ohms. I'll first find the PD across 50 ohms, which is going to be the current times the resistance. The current is 6, the resistance is 50, which is equal to 300 volts, which means the PD across 300 ohms, which is the same as the PD across the 60 ohms, is going to be 600 minus 300, which is equal to 300 volts. That is, if I remove the PD across this, which is 300 volts, the balance is the PD across the parallel combination. So if I want the current in C, is going to be the PD, which is 300, divided by the resistance, which is 300, which gives us 1 ampere. So without calculation, of course, the current through D is the PD, which is 300, the resistance, which is 60. This gives us 5 amperes. Okay. A wire of diameter D, length is L. So length L and resistivity rho forms a circular loop as shown below. A current enters and leaves the loop at points P and Q. So it means this current divides into two parts. One part takes this route and another part takes the other route. Show that the resistance R of the wire is given by the expression R equals to rho 4 rho x into L minus x. So if the total length is L for the wire, it means this part is going to be L minus x. Remember, we said the resistance is equal to rho L over cross-sectional area, and area is equal to pi d squared over 4. So this becomes 4 rho L over pi d squared. So I'll call the resistance of this side R1, I'll call the resistance of the other one R2. So R1 is going to be equal to 4. It is the same wire. The resistance, the length is L minus x divided by pi. Diameter is the same, d squared. Then for R2, it is going to be 4 times rho, the length is x, divided by pi times d squared because the diameter is the same. Now these are going to be like two resistors in parallel. Total resistance in parallel is the product over the sum. So it means total resistance is going to be 4 rho. Now let me write here. Total resistance in parallel is going to be 4 rho into L minus X divided by pi d squared times 4 rho X divided by pi d squared divided by 4 rho into L minus X over pi d squared plus 4 rho X over pi d squared. So in the numerator, I may have, let me first leave the numerator alone. I'll just leave it the way it is, and I just sort of simplify the denominator. So in the numerator, I may have 4 rho 4 rho into L minus X divided by pi d squared times 4 rho X over pi d squared. Then here the LCM in the denominator is pi d squared. So divide by pi d squared. When I open the brackets in the denominator, I have 4 rho L minus 4 rho X plus 4 rho X. So this one cancels with that. Now this one cancels with one of those. And I remain with the denominator. I only have 4 rho L. So I'm having 4 rho into L minus X times 4 rho X divided by pi d squared times 4 rho L in the denominator. So 4 rho can cancel, 4 rho cancels. Then we remain with the 4 rho, there is an X there, into L minus X divided by, I'm remaining with the pi d squared and 1L as required. So I just used the concepts of resistors in parallel, because two parts, if the wire current divides from here, the two parts of the wire will be behaving as if they are resistors in parallel. Okay, so you now qualify to solve all the remaining questions. I'll just show you the page and proceed. So self-check 2, you can just try out these questions. That is 1, question 2, question 3. Those are easy questions. Question 4, what is the effective resistance of the current? 4, 5, those are easy questions. Question 6 and 7, I think those are easy questions. Question 8, I think that one is also an easy question. Question 9 and question 10. I think question 10, the diagram is above. Question 11, 12, 13, and 14. These are just for your practice to gain a lot of confidence. (15, 16, and 17). Then question 18 19, 20, 21, and 22. And lastly, there is a consolidation homework. Of course, the process by which heat spreads through water, I think that is convection. The rest are easy calculations that we have already dealt with. Yeah, so I think this lesson has given a lot of practice questions for a serious student. And the last lesson, or the second last, I don't know whether it will be the last or second last lesson, which will be Kirchhoff's laws, is going to be the most important lesson, especially for the AS level physics. So see you in lesson 6, which is the most important lesson.